All right, so as x becomes huge, the base x becomes infinite, right? And what does the exponent turn into? 1 over something that's infinitely big should become really small, right? So this should head to 0. So we have something that looks like something is becoming infinite, raised to the 0 power. And what was the battle that created? What was the issue?
It's trying to go to infinity, but it's also trying to go to 1.
Yeah, so anything raised to the 0 should be 1, but then the bases really want to become infinite, so they're fighting each other, right? So let's see if they compromise or if one of them wins over the other one. So how do we do this? I mean, if this were infinity times 0, we'd be in business, right? Because we just drop one down. If it was infinity over infinity, or 0 over 0, we just go 0 over 0, we just go straight to L'Hopital. These are the only three we know how to handle right now. Agreed? So there's not a super easy way to make it turn into these. We actually have to do something with the natural log. So what we're going to do is we're going to take a look at this, and we're going to call this limit right here, we're going to call it y. Yes?
Real quick.
Uh-huh.
I'd forgotten, but what, well, like, and it's related to this, but what happens if you get, like, infinity raised to a power?
Then it would just be, I mean, like, if that power was just like 3 or something, it would just be infinity.
So, in this case, would we be able to write infinity to 0 as infinity to the negative 1 over infinity to the 1? Because then, if you, I know it's not the same, but if you like have x, if x is
You're saying, can I rewrite this as infinity to the
negative 1 over infinity to the 1, or just infinity?
like that?
Because, I mean, if you had, I know it's not the same, but if you had like x to the negative 1 over x to the 1, then they would,
That would be x to the negative 2.
or, sorry, then,
I think I know where you're going with this. Maybe I'm wrong, but continue.
well, I was just wondering if, instead of trying to find out infinity to the 0, you could try to find out like infinity over infinity or infinity.
I think I kind of catch what you're trying to say. Is there like a clever way I could rewrite this as using that sort of property? The fact that this is not a number, right? This is an expression with x in it, is really gonna prevent us from doing that. If this was a fixed number, then we could do it. But then we wouldn't be doing this anyway, because infinity to a number would just be infinity. Okay, so this is the standard practice for this. Okay, and this, what I'm about to show you right now, works for this, and shoot, I forgot, 0 to 0, okay? For these three indeterminate forms, the following procedure will hold for all of these. So what we'll do first is we're just gonna call this limit something, right? We can call it anything you want, but we're gonna call it y because, well, why not, right? Just call it y. So everyone agree, we wanna know what y is, right? That's what we wanna know, what's y? Now what we do is we take natural log on both sides, right? So natural log of the limit as x goes to infinity of x to the 1 over x. So that's just using properties of logs. We've done this before, yes?
So in this case, it's okay to add a y. Right?
I'm not adding a y. I'm just calling the limit that I'm looking for. I'm just calling it y. So, you know, I say, hey, we want to know what this is, right? So let's just call it y. If you want to call it m, call it m. If you want to call it t, call it t. I'm just going to call it y. So y is what we're looking for. I've created this equation so I can do natural log on both sides. And then there's a very important property of limits and natural logs that I stated in the very beginning when we first started talking about limits. They were part of the limit laws. Do you all remember me talking about the limit laws? The limit laws, way back when, this would be like the very beginning of class, the limit laws, said that if you have a limit inside of a function, you can pull the limit outside the function, basically. Or you could say that the natural log passes into the limit. So this is a property of limits and logs that is allowed, all right? All right, now why is that helpful? Yeah, now I can take this 1 over x and I can drop it out in front of the natural log, right? Okay, so I have natural log of y. Notice I keep on writing natural log of y in the right side. Just keep writing this equation all the way down. Limit x approaches infinity. Now I had the 1 over x came out front, and then times natural log of x, right? That's what I have. And look at this. Right now, if I check, as x goes to infinity, what's 1 over x? 0. Natural log of infinity. What does the natural log function do as I go out to infinity? It goes up to infinity. So what's happening here on this side is this is going to 0 times, and this is going to infinity. Make sense? Now, how do we handle 0 times infinity? Drop 1 down, right? So see, this whole process of creating the equation and taking natural log on both sides allows me to drop the exponent down. If I drop the exponent down, I'm guaranteed to have 0 times infinity, and now I can just go back to what we just talked about. So let's do this. I'm going to drop 1 down. Now, the one I drop, I'm actually going to rewrite the 1 over x. So, like, I guess technically I am dropping it down, but really, I can just rewrite that as this, right? I mean, that's the same expression. Like, this is the same as that. Checking it real quick, x goes to infinity, we get infinity over infinity, right? They both go to infinity, so I can use L'Hopital's rule now. So I do L'Hopital's rule. So what I say is natural log of y is equal to the limit as x goes to infinity. I'm going to put a little L over my equal sign to let everyone know I'm using L'Hopital's rule here. And now I do derivative of top and bottom separately. So what's the derivative of the top? 1 over x. Derivative of the bottom is 1. So that's just 1 over x, right? And now let x go to infinity.
0.
You get 0 on the right. So what we get here is that the natural log of y is equal to 0. That is not our answer. Because remember, we called this thing y, didn't we? We said, hey, we want to know what y is. Right now we know what natural log of y is. So back from college algebra, if you want to get something out of a natural log, you have to come in here and bring the inverse function in to kill off the natural log. So what's the inverse of the natural log? E. So I'm basically going to be composing both sides with e, and I get this. I'll write the step down, but I'm doing e to the natural log of y equals e to the 0. So I'm just really just doing this. I'm doing like e to the left side equals e to the right side. And the whole reason for that is this will kill off and you just get y. And you get e to the 0, which is 1. So the answer here is 1. The limit as x goes to infinity of x to the 1 over x is 1. So the further out you go, if you were to graph this as a function, the further you draw it to the right, the closer and closer it gets to 1. Yes?
I guess I'm not understanding which part do I just go ahead and drop underneath? Like, I guess it's just still not catching into the.
I think.
How do I know? I got this one versus this one.
I don't think that there's really like this rule of thumb, like that you always. I think you have to look at both of them and decide which would you rather take the derivative of. Like, okay, so like when we were back here at this step right here, no. We were at the step where we had limit, x goes to infinity, and we had 1 over x times natural log x. Right, we were there, and I decided to put the x on the bottom. What if just you wanted to come in and you wanted to do this? Take this one and drop it. Okay, so you leave the 1 over x on top, and on the bottom you have to put what? 1 over ln x. Okay, now, derivative of top and bottom separately. Derivative of this top would just be negative 1 over x squared. Derivative of this would be a quotient rule, because that's 1 over the natural log of x. You can't do derivative of top and bottom separately. You have to do it as a quotient rule, and that would be a mess. Not a mess, but it wouldn't be nice. And then not only that, if you did it, I'm guessing it would just get more complicated. Does that help?
That doesn't.
Okay, okay. All right. Let's do another one. You might like this one. I want us to find the limit as x goes to infinity of 1 plus 1 over x raised to the x. And I'm going to put a little star next to this problem because, like I said, after I'm done with this, you're really going to like it. And even if you don't like it, I'm going to make you tell me you like it, even if you don't like it. It is possible. Wait, see what happens at the end. And like I said, I think you're going to be a little bit like, whoa, okay. A little bit. All right, so here we go. What is the form that we're getting here? So as x goes to infinity, 1 over infinity is headed to where? That's headed to 0, okay? What's 1 plus something that's headed towards 0? It's headed towards 1, right? So do you agree everything in the parentheses is headed towards 1? Is it 1? Ever is it 1? No, it's never 1, but it's getting close to 1, yes? Okay, so my base is headed to 1, and then the exponent is headed to where? Infinity. And this is bad because even though the base wants to be 1, it's not 1. And the exponent keeps on trying to multiply times itself, so it tries to like make it get bigger, right? So let's see what happens. Well, we can't go straight to L'Hopital's rule. The fact that we have this exponent thing happening, we don't have like 0 times infinity, means that we're going to have to bring the natural log in on both sides. All right, so first thing we'll do is we'll call this something. We'll call it y. So are y'all understanding that this whole idea of like bringing in the y equals this and then doing natural log, the thing that tips you off that you're going to do that is when you have one of these 3 forms, when they look like something to a power, something to a power, right? When that happens is when you'll do this. Yes? Okay, so now we do natural log on both sides. Now on this step, I'm actually going to do the natural log, but because I know the property of logs, or property of limits, I'm going to go ahead and just push that natural log already through the limit. So I did natural log over here. Instead of writing it on the outside, I just wrote it on the inside, okay? Because that would have been my next step anyway, is to move it inside the limit. What would be my next step?
Turn the x down.
Drop that x down. So natural log of y equals limit, x approaches infinity, and then I have x times natural log of 1 plus 1 over x. And now let's do a quick check to see what we've got. As x goes to infinity, this part's infinite, right? Infinity, so that looks like infinity times. Okay, 1 over infinity we said went to 0. 1 plus 0 goes to 1, right? But now we have natural log of 1, and the natural log of 1 is 0. So this is looking like infinity times 0. Questions?
We can't confirm that yet.
Pardon?
We can't confirm that yet.
Yeah, we know that this is headed to infinity, and we know this is headed to 0. But we're happy about that because when we have that situation, we know we can just drop 1 down. So what would you rather drop down, the x or the natural log of 1 plus 1 over x? Probably the x, right? Okay, so natural log y equals limit, x goes to infinity, of natural log of 1 plus 1 over x over 1 over x. So just taking that x and rewriting it as 1 over x in the denominator. Okay, now can I break out L'Hopital? Yeah? I can break out, thank you. I can break out L'Hopital, right? And you want me to sing it? I can sing it. Okay, limit, x goes to infinity. Okay, so be careful here. The derivative of the top requires chain rule, right? Derivative of natural log of something is 1 over it. So I'm going to put 1 over 1 plus 1 over x. Okay, that's the derivative of the natural log of this, but then still what do I need to tack on to the end of that? times the derivative of what's in here, right? So derivative of 1 is 0. Derivative of 1 over x is negative 1 over x squared. So tacked on to the side of this, I have negative 1 over x squared. That's just the derivative of the top. Y'all clear? Okay, over the derivative of the bottom, which is negative 1 over x squared. And this looks rather complicated, doesn't it? Just looking at it. But do y'all see what happens? This cancels out. Gone, gone. And now let's just run a quick limit on this and see what happens. As x goes to infinity, 1 over infinity goes to 0. 1 plus 0 is going to 1. And 1 over 1 is 1. Right? So this limit now, because these are gone, this limit, that limit is just 1, isn't it? Just 1. So what we have is that the natural log of y equals 1. But we're trying to solve for y, not natural log of y, right? So we come with e on both sides, e to the left side, e to the right side. So e to the natural log y equals e to what power? 1. And so the left side is y and the right side is just e, right? So what I'm saying to you is this, that e is defined to be the limit as x approaches infinity of 1 plus 1 over x raised to the x. That's the definition of e. Like if you ever want to know what e is, that's what it is. That's weird. Okay, so what? What in the world is he saying? Okay, so what I'm saying is this. We're done with the problem, right? We have the answer is e. But the more profound thing here is this. If you go to your calculator right now and you type in e, somebody do it on their calculator, you're going to get what? 2.718 something, right? Right? Okay. What this is saying is that if you'd like to know what e is, what you need to do is look at this expression and let this number get infinitely large. So for example, a large x value here would be maybe like 1,000. Let's go with 1,000. If you go to your calculator right now and put 1 plus 1 over 1,000 and raise that to the 1,000th power, I want someone to tell me what they get. $2.716. Okay. All right. That's not e. E is 2.718, right? Okay. So, but 1,000, is that really that big? I mean, we're supposed to go to infinity, right? So let's try something else. Let's go 1 plus 1 over, let's go to 1,000,000 and raise it to the millionth power. So I need someone on their calculator to do that and tell me what they get. 2.718, and then there's more decimals probably after that, right? And that would be a very good approximation of what e is. But if you want to get even better, you just let this number get bigger. And if you want to get even better, you just let it get bigger. So the more decimal points like you want as far as being accurate, you just change this number to a bigger and bigger number. So you can always go out as far as you ever need to with e, provided you're willing to plug big numbers into this. If it was possible to go to infinity, then you would reach e, but you can't reach e. You can't ever reach it. Does that make sense? It's weird. So I'm going to just show you the graph of this function because I think it's worth seeing it. So I'm going to graph 1 plus 1 over x raised to the x. Man, my window's all messed up here. I'm blowing this for later. There we go. So All right, that'll just have to do. So here's the function. Starts out over here, climbs up, and then it asymptotically approaches. So there's a horizontal asymptote right here that our function is getting closer and closer to, right? Like this dotted line, and we're getting closer and closer to it. That dotted line that it's getting closer to is e. So the further you go out, the closer it gets to that. Okay? It's kind of weird that we can define a number as a limit. It's probably the first time you've ever seen that in your life, where we define a number as a limit. There's other numbers that we've talked about that are important in our class, like pi, right? Pi is an example of an irrational number like e. It has the same property in the sense that this is a non-terminating, non-repeating decimal. But pi has a very simple definition. You don't need a limit to describe what pi is. All you have to do is say, hey, it's just simply the circumference of a circle divided by its diameter. Give me any circle, measure the circumference, measure the diameter, little d, take the ratio of those two, and you're going to get pi. Very simple definition. Definition of e, not so simple. All right. Do you feel like from those two examples you have an idea of how you would handle like that indeterminate forms with the powers? Yes?
I'm only asking, have you ever had students who try to tackle more difficult choices, like choice 1, choice 2?
Choice 1. You mean like as in terms of which one to drop down? I do have students that drop the wrong one down, and usually the mistake they make is they oversimplify that derivative of top and bottom. Like the example I gave earlier, where we said we could have left the 1 over x on top and 1 over natural log of x like that. Students will do that, and then what they'll do is they'll do the derivative of the top, no problem. But then when they do this, that's 1 over x. So all they did is they didn't even do derivative of the top, they just left it alone. They did derivative of natural log, which is 1 over x. This is wrong. So that's what I usually see is they do this, but then they make this mistake here. When you do your homework problems, hopefully you'll start to pick up on which one should get dropped. I mean, you only have 2 options. So if one of them gets bad, go to the other one, right? All right. The last indeterminate form we need to look at is infinity minus infinity. It's the last one. So we'll start with a pretty simple one. Let's say we have the limit as x goes to infinity of x squared minus x. This is the most basic example that we could probably come up with. So we do have something that's becoming infinite, right? Minus something that's becoming infinite. So we do have infinity minus infinity. You do not need to really, in this problem, you don't need to worry about trying to get it to look like 0 times infinity or anything like that. All we're going to do here is factor. Okay, we can factor this, can't we? Okay, so if we factor that, we'll get x comes out, and then we have x minus 1. And now, if you look at this, this goes to infinity. And then what about infinity minus 1? It's infinite, and we're multiplying those, right? So infinity times infinity is infinity, right? You have something getting big times something getting big. They help each other out. It becomes big. This is infinite. Yeah? So answer here, infinity. What? Yes? Yes.
Like always just like limits me. First we just get rid of the x equal infinity and see like.
Yeah, see what happens. See the behavior. Now what if this had been a plus? Well, then we would have done anything. We would have just said infinity, because infinity squared plus infinity would be infinite. It's the minus where you don't know who wins, right? So let's try another one. How about this? X minus e to the x. All right, do we have infinity minus infinity? As x becomes infinite, that's infinite, right? Minus, what's e to the infinity? What does the e function do as you go out to the right? It goes up to infinity, right? So we have infinity minus infinity here. Now what did we do on the last problem when we had this? We factored, but there is no common factor here, is there? Do y'all agree? There's no common factor. So, okay, so you might be thinking log because that would help with the x. How about I force you to factor? How about I tell you factor? You have no choice. I force you to factor that. I want everyone to factor an x out. X comes out. What are you left with right here? Okay, minus what's there? E to the x over x. Okay, why is that true? It's not cheating. This is smart. This is smart. So see, if you distribute that right, you get back this, right? Do y'all see that?
So we haven't done this derivative yet, right?
I haven't done anything. All I'm doing is rewriting the problem right now. Do y'all buy that? Okay. So now let's just check real quick to see what happens. If I let x go to infinity, where's that going? So I'm getting something that looks like this. Infinity times. Okay, now in here I have 1 minus now what? Infinity divided by infinity. L'Hopital. So I'm going to come over here on the side real quick, and I'm going to say what would be the limit as x goes to infinity of e to the x over x. Do you see? This part right now, I need to figure out what it's doing. Okay, I need to figure out what is this doing as x goes to infinity, so I come over here to do that work. But I'm not too unhappy about it because I have infinity over infinity. And so I can go straight to L'Hopital's rule on this little piece. Yes or no? Go back one?
Yeah, I like you.
Okay. You're okay with me factoring out x? Okay. You're okay with that going to infinity?
That's what I like.
X going to infinity, so that going to infinity, right? Parentheses 1 minus. Now, e to the infinity is infinity over infinity, right? This is infinity over infinity, and I don't know what that is, right? Anytime we have infinity over infinity, the answer is I don't know. So I've got to go figure out what exactly that's doing. But because it's infinity over infinity, I use L'Hopital. So I just run a quick little L'Hopital over here. Limit x goes to infinity. Derivative of the top, e to the x. Derivative of the bottom, 1. And now I no longer have infinity over infinity. I have infinity over 1. And infinity over 1 is just infinity. So this limit is going to infinity. Got it? Okay, now we come back over here. We said this was going to infinity. And then this piece is going to 1 minus that, but that's going to infinity. So 1 minus infinity. 1 minus infinity is negative infinity. And I'm multiplying these two, negative infinity. Yes?
How are you able to use L'Hopital's rule, like in the equation, and it doesn't alter like the rest of it?
Okay, so L'Hopital's rule is that L'Hopital's rule doesn't care where you are in the universe. It just says anytime you see an expression that has infinity over infinity or 0 over 0, if you want to know what's happening, you just take derivative of the top and bottom and look at that new limit. If that's part of a bigger problem, then fine, just go look at that little piece. It doesn't care, because L'Hopital's rule is kind of, I don't know another way to explain it other than this limit is saying let these x's become huge, right? If at any point in time you don't know what any of this is, but it qualifies for L'Hopital, you just go do it. Not sure I have another explanation. Questions? Any other questions? So negative infinity here? So our answer is negative infinity. Does it make sense that it would be negative infinity as an answer? Like which of these functions is more powerful as you plug in bigger and bigger numbers? The linear function or the exponential function? The exponential function should overpower this pretty easily, right? Yes?
So now you got e to the x over x.
Yeah.
It's up to infinity. log go to infinity as well?
Here? Yes, it does.
Okay.
But then that's because this goes to infinity up here, and this goes to infinity here, that's why I can use L'Hopital's rule on the next line. Then I get something that is no longer indeterminate. Okay, one more. Limit x goes to 1 from the right of the natural log of x to the 9th minus 1 minus the natural log of x to the 6th minus 1. That looks pretty bad, yes? Okay, let's first see what's happening, right? As x approaches 1, 1 to the 9th power should be close to 1, right? Minus 1 should be approaching 0, and then natural log of 0, which is headed to negative infinity. So that's headed to negative infinity. Agreed? Okay, so this is headed to negative infinity. And then we have minus. Now let's do it again over here. We're approaching 1. 1 to the 6th power is approaching 1. 1 minus 1 is 0. Natural log of 0 is headed towards negative infinity also. So I have minus negative infinity. So that's the same as negative infinity plus infinity, right? Which is indeterminate. Negative infinity plus infinity. Who wins? Who wins, right? So now in this one, I'll give you a hint. I would not factor.
They go, you take the natural log of x over 9 minus 1 over x.
So push them into one log?
Yeah.
Yes, that's the way to do it. So we have two logs with subtraction, right? Why don't we condense those into one log with division? So limit x goes to 1, of a single natural log expression now of x to the 9th minus 1 over x to the 6th minus 1. Okay, that's just a property of log. That's all that is, right? Some algebra. And now let's try our limit again. Yes?
You're just gonna go the other route, like, is it like the question started with x over 9 minus 1 over x to the 6 minus 1? So you've gone, it's like vice versa. It's like so there's some questions with more solutions that start off with fractions. So you just use the algebra.
Well, did they have natural logs in them though?
Some kind of like vice versa in a sense.
I'd have to see what you're referring to before I can confirm or deny. All right, so I was just following the guide here. So what now?
I want to first check.
What happens?
Yeah.
Okay, so if we let x go to 1, we get 1 minus 1 over 1 minus 1. We get 0 over 0. So this is what we were talking about a second ago. We're getting a 0 over 0 now, right? Which is L'Hopital. So I'm going to go to the side over there, and I'm going to figure out what's happening to this as I let x go to 1. I don't care that it lives in a natural log. I'll deal with that later, okay? So over here on the side, I'm going to figure out what is the limit as x approaches 1 from the right of x to the 9th minus 1 over x to the 6th minus 1. And we've actually done this a few times now where we had 0 over 0. We just do derivative top and bottom separately, right? So using L'Hopital, limit x approaches 1 from the right, derivative of the top, 9x to the 8th, derivative of the bottom, 6x to the 5th, right? Yeah, and we can say that that's the same as the limit as x approaches 1 from the right. Just reduce things, right? Like and kill off like 5 factors of x, reduce that to be 3 halves, right? 3 halves x to the 3rd power. And now let x go to 1. And what do you get? 3 halves, right? 3 halves. So what I can tell you right now is that when I take the limit as x approaches 1 of this expression, this inside is headed to 3 halves. And then I'm taking natural log of it. So my answer is natural log of 3/2. So that's an example of a very strange result. Like we have something that is getting infinite but negative. We're subtracting something that's becoming infinite and negative. So we say who wins? Well, in this case, they compromise and they settle on natural log of 3/2. That's what they decide they're going to go to. Okay. Questions or comments or concerns, complaints? If you have any complaints, contact Isaac Newton and Leibniz. Yes? The ln eliminated the x cubed? No. On the limit I just erased, I had limit x was approaching 1 of 3/2 x cubed, right? You were okay up to there? Now let x go to 1. So 1 cubed is 1, so you just get the 3/2. All right? Okay, the rest is up to you in terms of homework for this section 3-7. You should be able to, do I say stop at 33? Last time I did, right? 33. I mean, it would be worth your while to go all the way to 38 on this.
I think in the homework video, you said you do all the
Yeah.
Like even in odd numbers, all that?
Well, I mean, if I were you and I wanted to do well, I would practice every problem I could up through number 38. That's what I'm saying. Like, if I say just do the odds, you can just do the odds, but if you do the evens, you're better off. I think you just more practice. So when I was a calculus student, I didn't get serious about calculus. I didn't get serious about math until Cal 2. That's when I started to get really serious. And the way that I went about Cal 2 is every night I would try and read the section we were supposed to cover before class. And then I would try and do every homework problem that, so the professor would give us in the homework set, I would do like every problem that he skipped, or, you know, I tried to do every problem. And I've gone back and looked at my work, and like, majority of it's wrong, okay? But I tried every problem, you know? And so there's something to be said for at least trying to do the problems. Just things get burned in better that way. I don't know. Okay, you ready? We're going to move chapter 4. Y'all excited? What's that?
I said, make sure your algebra and trig is strong.
Yeah, you know. Yeah, it's hard to, that stuff takes a while to get good, real good with. What am I doing? Chapter 4. So I'm just going to show you this real quick. Chapter 4, applications of differentiation. So finally we get to start doing something with this that hopefully you'll find somewhat useful. And I thought we would motivate this by not just getting right into the lecture notes. I thought I'd put a word problem up here for us to consider. All right? So this to me seems like a reasonable, real-world problem. You may not find it's reasonable, but let's say that this is a top view. Let's say that I have some river. Okay, this is a river. Okay, and let's say that I have a building over here, building A. And across the river, downstream, or upstream, however you want to do it, we have building B. And we have to hire a company to come out here and run some fiber optic cable between the two buildings. All right? Now I need to give you a little more information. I made up this problem before class, but I want it to work out a certain way, so let me copy down what I had. The river, the body of water we have to go across is 200 feet wide. And the distance downstream from building A down here to building B, where we're going, is 1,000 feet. Okay? Understand so far? I need to connect building A to building B with fiber optic cable. I'm going to hire a company to do that. Let's say that you're the company that I'm considering. All right? And you have to figure out how much it's going to cost you to run that cable. Still with me? Okay, now, for you and your company, y'all are like experts at running fiber optic cable. But there's a difference between running cable through ground and running it underwater. Nothing can be above ground, okay? That's part of the contract. Everything has to be buried, all right? So when you bury, your company has already figured that it costs $500 per foot for underwater cable burial, okay? And it costs $300 per foot to go underground. It should be a little cheaper to go underground, right? Because your conduit, doesn't necessarily have to be subjected to moisture as much. I mean, there's different considerations. You can just dig underground, right? You don't have to worry about other issues. When you go underwater, that's a little different. Y'all follow? So the question here is, you have to propose this bid, right, to me, because I'm going to hire it. I've got different companies bidding on this, okay? So how are you going to determine the bid to me? What number are you going to throw at me as far as how much it'll cost your company to run that cable? Let's talk about this. Come on, what do you think?
Now we wanna find out how
300,000.
far.
What's that?
300,000 just from A to B on the ground, like lengthwise.
If we went from A, you're saying all the way downstream,
Yeah.
that would be $300,000?
Yes.
Okay, and then if we went from there straight across, would be 200 times the 5, so that would be what?
10,000.
What'd you say?
10,000.
10,000. I thought you said 100,000. I'm sorry, I misheard. So we said 300,000 to go this across. Agreed? And then plus 200 times the 500, so another 10,000 go this way. 100,000. 100,000? Yeah, 4 zeros. Yes? So is that your proposal?
Well, I was going to say that's the way to get it with the least underground, or with the least in the water.
Okay, so I'm going to put that up here. I'm going to draw this in red. One proposal could be to go, this is the path of the fiber optic, across and then down, like that, right? So you will do $300, right, times how far are we going above, underground but outside the water? 1,000 feet, plus then $500 and you're going straight across, so 200 feet. And what's that grand total? $400,000. That's your bid, okay? Well, you don't have to stick to that, but that's one bid, right? Anyone else have another bid?
$287.
Where are you getting that number from?
Made it up.
You made it
But
up?
I do have an idea of what the actual thing should be.
Okay.
You're not going to go all the way down to the edge. You're going to find a point at which you can go down underground for A, cut off somewhere right maybe there, and then go across the B.
So so that, maybe we could go down a little bit and then go across. So the red is one extreme. As far down as we can go, straight across. This minimizes the underwater, but it kind of we get the maximum in the ground, right? The other extreme would be shortest distance. Shortest distance is just straight from point A to point B. It's all underwater though, right? So let's look at that idea. We're just going to go straight. Shortest distance. So do we know what that distance would be? We could figure it out because this is a right triangle, right? So let someone on their calculator do this. This should be, well, I'll get mine out. That should be the square root of 1,000 squared plus 200. Someone's getting that for me.
10, 19, 8.
10, 19, 8, and some change maybe, right? 1019.8. Okay. Yeah. 1,019.8 feet, something like that. So what would that cost? That'd be 1019.8, but it's all underwater. So how much would that be? 500. So what's your cost? What is it? 500.
509,901.
They don't get the bid. They don't get the contract, right? They don't get the contract. So far, the Reds got the better proposal. Yes.
It seems like you would want to go like maybe 800 feet on land,
Mm-hmm.
and then the rest.
And then the rest of the way here. So do you all understand? These would be two extremes. One of them is obviously better than the other. But there might be some combination in between where you get the best result, the cheapest price, right? How do we find it? You're saying maybe 800, you know, but how do we find that? So let me just help kind of guide us through this. Let me get blue here. The other kind of middle of the road idea would be, let's go down a certain distance, right? Let's go down a certain distance, and then from there, let's cut across straight to B. Now, how far I actually go down, I don't know, right? So let's call that X. Okay? It's not going to turn out like that. Just, yeah. Hang tight. If that's X, then so far my cost is going to be what? This distance, X, times what? 300. So far my cost is 300 times X, but then plus, now I need to go from here to here, right? From here to here. Do we know this distance? It is no longer 1,019.8. The distance from here to here is based off of a different triangle. It's the triangle that goes up and over and like this, right? Okay, do we know this side of the triangle? 200, that's not changing. Do we know this side of the triangle? It's 1,000 minus X, right? Because if X takes you from here to here, this is 1,000 minus X. Agreed? And so this side right here should be the square root of that squared plus this squared. That's using the Pythagorean identity, or Pythagorean. So that side should be the square root of that side squared plus that side squared. Understand? And that's this distance. And how much do I pay to go across that distance? 500. So my cost will be that plus 500 times the square root of 1,000 minus X, that quantity squared, plus 200 squared. That's it. That is my cost function. That is my cost function. If you tell me what X is right now, I will give you the cost. You follow me or no? Okay, so if X is 0, then we're going with the purple, right? And so the cost, if X is 0, our cost should be 509,000. What happens if we plug 0 in here? Gone, right? If we plug 0 in here, we get that purple triangle, or yeah, the purple one. And then we multiply times 500, so we'll get that number. What if we go all the way downstream? What's X? 1,000, right? And if X is 1,000, this is gone, right? Would this be gone? Gone, and so all we get is 200 squared under a square root. What's 200 squared under a square root? 200, so this is 200 times 500. That's this piece. And then this is 300 times the 1,000. That's that piece. This formula takes into account everything, all the different scenarios. So, what if we graph that function? What if we graph it? Let's graph it. And I need to change my window here. Here it comes. Where is it? What happened? What were my costs? Underwater was what, 500? And under the ground was 300. Okay, what you're looking at right there is a picture of that graph, all right? I'm going to erase all this crap out of here. That is a picture of the function I just put up there. What point on that function are we interested in? The lowest point on that function, right? The lowest point on that function. This is between 1,000, right? Here's 0. Remember, x was the distance we go downstream, right? I think you go past 1,000, then you shouldn't have a company, right? Okay, so from 0 to 1,000, right, is where we're looking, and we're trying to find the lowest point on this cost function. So we said when x was 0, we're going all underwater, and that's this. There's 400,000, 500,000, it's a little more than 500,000 do that. When we let x be 1,000, we went all the way downstream, we got this extreme down here, okay? But that's not the cheapest. The cheapest is somewhere in here. Somewhere in here. What is it? Well, I can tell you right now, it's 850. At 850 feet downstream, we will get the lowest point on the graph, and it will cost us 380,000. Right? 380,000. That's the cheapest we can do it for. Now, how is this tied to anything we're doing, that we've been doing? How is this tied to it? Were we able to take that word problem and turn it into a function? Yes? And what are we looking for on that function? The lowest point. And do you recognize that on the lowest point of any function, what the slope of the tangent line is going to be there? 0. 0, right? So that function that I put up here a second ago, I could look at it as a cost function. Right? It's like a function, right? And I want to know the lowest point on that. So I'd like to know, when do I get a tangent line that has a slope of 0, right? Which means I need to take this and do what with it? Take its derivative and set it to 0. If I can take the derivative of that and set it equal to 0, I should get an answer of 850. I'm going to do it right now. We're not ready for this because, not ready, but we have a whole section on application problems, but I'm trying to show you what we're leading to. All right, we want to be able to do this. So I'm going to take the derivative right now. It's not going to be that pretty, but we can do it. What's the derivative of 300x? Just 300. I'm going to get the, whoa, what happened there? Whoa. I'm going to get this out of here. So derivative of that is just 300, that's the easy part, plus 500 is a constant, it will come for the ride. What's the derivative of the square root of something? 1/2 square roots of all that junk. I'm not going to put it there because I'm going to rewrite this in a second. But when I say junk, I mean everything in there, okay? Okay, am I done with the derivative? Nope. I now need to multiply that times the derivative of what's inside of here. So I have to do derivative of this one separately. Derivative of that one's just going to be 0 because it's constant. Derivative of that, chain rule. 2 comes out first. 2, 1,000 minus x to the first power times -1, which is the derivative of what is inside of it. Do you see all that chain rule happening? All right, I'm going to clean that up. So this is where we had done like raw derivative, right? I said at some point we have to set this equal to 0. The day has arrived. Okay, so now I'm going to take this expression. This is 300 plus, let's see, has any of this clean up? These 2's are gone, right? This minus right here can go there, right? Actually, you know what I'm going to do? I'm going to pass the minus through here. Okay? That'll be a positive x and a minus 1,000. Right? And I'll still have a 500 out front. Okay, so I'm going to have plus 500. And then I said I'm going to have a positive x and a minus 1,000 on top. And then what's on the bottom? Square root of all that junk, right? Would you all agree that that's the derivative? Kind of cleaned up a little bit? And what do I want to know about that derivative? When it's equal to 0. So when is that equal to 0? Because that'll tell me where the slope of my tangent line is 0. And that should tell me where it corresponds to like a lowest point on the graph. Hopefully there's only one answer to this. We'll see. Hopefully there's only one solution. So how do I go about doing this? How do I set that equation equal to 0? Well, the first thing I'm going to do is I'm going to get a common denominator between these two. Okay? I'm going to get a common denominator. And if you're freaking out, don't freak out, because we are going to go through this with easier functions to start. Okay? I wanted to give you a nice word problem to start because it's actually, I think it's better to start with something that looks useful. Okay, so all I did was we got a common denominator. So I wrote this as over 1. I put root junk here, right? Root junk top and bottom, and then I smashed them together. Now, little side note, but very important. If you ever in your life have an equation where you have a fraction is equal to 0, you don't ever have to look at the denominator. Why? If I multiply both sides by b right now, they cancel and you just get a equals 0. So anytime a fraction equals 0, anytime a fraction is equal to 0, you only have to look at where the top is equal to 0. That's nice, because then I don't have to consider this junk down here anymore. So my next line should look like this. 300 square root of the junk plus 500 x minus 1,000 equals 0. This looks terrible. Questions? I'm about to put all that junk back in. Yeah, I just wanted to get us at least to that point, all right? So I'm now going to write the next line. How do I want to do this? Okay, I'll do this. Square root of 1,000 minus x squared plus, it was 200 squared, right? Which is 40,000. I'm going to go ahead and square that now. Equals negative 5/3 times x minus 1,000. Okay, so what did I do here? I moved all this to the other side, which made it negative, right? And then I divided everything by the 300 that's in front of the root junk. And so what happens is the negative 500 over 300 become 5/3, and then I still have this out here. Is that fair? What do you think I'm going to do now? Square both sides. I wanted to get rid of the root, so I'm squaring both sides now. And when I square the left side, I just get 1,000 minus x squared plus 40,000.